Time is not what it seems. Every second you feel passing, steady, predictable, is an illusion woven by your perspective. Because under the rules of relativity, time bends, stretches, and sometimes nearly stops. Imagine falling toward a black hole. From your perspective, your heartbeat stays steady, your watch ticks normally, your breaths remain calm. But to someone far away, watching you from a safe distance, you appear to slow down. Your motions stretch longer, your signals arrive weaker, until at the very edge of the black hole, the event horizon, you freeze. To them, you never cross the boundary. To you, you pass through without hesitation. This paradox is the bizarre physics of time dilation. We have measured it on airplanes, in satellites, even on mountaintops. But near a black hole, the effect becomes so extreme that reality itself seems to split. What does it mean to live in a universe where time is not absolute? What happens if you fall into the ultimate trap of gravity, where seconds turn to eternities, and the future arrives before you can return? Tonight, we will journey into the physics of time dilation, a path that leads us from Einstein's equations to the edge of black holes, and perhaps to the end of time itself. Now prepare yourself, because the closer we move to the horizon, the stranger time becomes. Part 1. Time as we know it. Close your eyes for a moment and feel the seconds pass. One breath in, one breath out. The rhythm seems steady, inevitable. This is how humans experience time, as a constant flow, one second following another. Our daily lives are ruled by clocks. A second defined with exquisite precision by the oscillation of cesium atoms. A minute, 60 of those seconds. An hour, 60 minutes more. And above it all, the grand clock of Earth itself. A full rotation marking a day. A complete orbit around the sun marking a year. We are so used to this system that we mistake it for nature's truth. But it is only one way of measuring. To ancient people, time was the sun's rise and fall, the turning of the seasons, the rhythm of planting and harvest. To them, time was not a number but a cycle, a circle endlessly repeating. Yet whether we call it cycles or seconds, we treat time as absolute. The same for everyone, everywhere. If your watch and mine both tick at 1 second per second, then surely the universe agrees. But already, cracks appear in this assumption. Even in our everyday world, time is not perfectly steady. Clocks placed on mountaintops tick faster than clocks at sea level. Astronauts aboard the International Space Station age slightly less than their twins on Earth. Tiny effects, but real, measurable, undeniable. And here begins the strangeness. Because if even small changes in speed or gravity can bend time, then what happens near the strongest force in the cosmos? A black hole where space curves infinitely, and time itself begins to fall. Before we dive there, we must first ask, what is time? Is it an arrow always moving forward? Is it a cycle forever repeating? Or is it something deeper, a dimension woven into the fabric of reality? For most of history, time was seen as absolute. Isaac Newton, the father of classical physics, declared it flowed evenly everywhere, independent of motion or matter. Like a great river, carrying all events within it. But Newton was wrong. The river bends, its currents twist, and relativity reveals a truth stranger than imagination. In this part, we will slow down, to feel the weight of seconds, before watching them unravel. But if Newton's vision of absolute time has faded, what remains is the human feeling of continuity. You wake, eat, work, rest, sleep. The rhythm feels unbroken. Yet physics tells us that underneath this rhythm, time is elastic. Imagine two people. One remains on Earth. The other boards a spacecraft traveling close to the speed of light. When they reunite, Their clocks disagree. The traveller has aged less, while the one who stayed has moved farther ahead. This is not theory alone. It has been tested with atomic clocks flown on airplanes and with astronauts orbiting above our heads. The realization is profound. There is no universal now. Your present and mine, separated by speed or gravity, may never align exactly. And so, time is not the rigid framework Newton imagined, but a fabric woven together with space. Einstein named it space-time, and in its weave, motion and gravity tug at the threads, reshaping how events unfold. Still, in our daily lives, the illusion of constancy holds. Your heartbeat does not change when you climb a hill. Your watch does not feel heavier when you board a plane. The deviations are so slight that only the most delicate instruments can detect them. To live as a human is to swim in the shallows of space-time, where the currents are gentle, but venture into the deep, into the gravitational whirlpool of a black hole, and those gentle currents become riptides. Seconds stretch into eternities. Distances collapse into points. The familiar rhythm of time begins to fracture. And so, this first part leaves us with a paradox. We live as though time is fixed, measured by clocks and calendars. But physics whispers that each tick of a clock is personal, bound to where you stand and how you move. Time is not one river, but countless streams, each flowing at its own pace, sometimes faster, sometimes slower, all woven into the great ocean of space-time. To understand black holes, we must first accept this truth, that what we call ordinary time is only local, fragile and relative. And with that, we are ready to step closer to Einstein's revolution, a vision where space and time are no longer separate, but two sides of the same strange fabric. Part 2. Einstein's Relativity. At the dawn of the 20th century, physics seemed almost complete. Newton's laws described motion. Maxwell's equations described light. Everything appeared to fit. But there was a problem. Light refused to obey. When scientists measured its speed, they always found the same value, 297,792 kilometers per second. It did not matter if Earth was moving toward the source, or away from it. Unlike sound, which quickens in the wind, light was absolute. This stubborn fact forced Albert Einstein to rethink the foundations. In 1905, he proposed the special theory of relativity. Its first rule: the laws of physics are the same for all observers in uniform motion. Its second: the speed of light is constant no matter how you move. From these two principles came consequences so bizarre that even Einstein hesitated. Time itself must stretch or shrink depending on your motion. Distances must contract. Mass must increase with speed. It was not an optional add-on. It was the only way to keep the universe consistent. Imagine a train rushing past at nearly the speed of light. From inside, the passengers see their clocks tick normally. But to you, watching from the ground, those clocks tick slower. Their heartbeats lag. Their voices stretch. They live in slow motion, but only from your perspective. This was the first revelation. Time is relative. No single clock rules the cosmos. Every observer carries their own measure of reality. But Einstein did not stop there. 10 years later, in 1915, he unveiled the general theory of relativity. Here he showed that gravity itself is not a force pulling objects together, but the bending of space-time. Planets orbit stars because the stars curve the fabric beneath them. And time tied into that same fabric is bent as well. Clocks run slower in stronger gravity. Seconds lengthen near massive bodies. What seemed like fantasy became measurable truth. And in the depths of a black hole, this bending of time reaches its ultimate extreme. But relativity is not just a theory written on paper. It is tested every day. The global positioning system, the network of satellites circling Earth, depends on relativity to work. Without adjustments, the clocks aboard those satellites would drift by nanoseconds each second, and within hours, your GPS location would be off by kilometers. Only by correcting for both special and general relativity does the system remain precise. So every time you check a map on your phone, you're using Einstein's equations. Every direction you follow is a quiet triumph of relativity. But relativity is more than practical. It is philosophical. It tells us that reality is woven from perspectives. Your now may not be my now. Your seconds may not match mine. And yet, both are true, both are real, both are part of space-time. This challenges our instincts. We want time to be universal, absolute, unquestionable. But relativity shows that truth is more subtle. It is a tapestry of viewpoints, stitched together into a larger whole. And in that tapestry, gravity is the master weaver. The greater the mass, the deeper the curve in space-time. The deeper the curve, the slower the clock. A mountain peak ticks faster than a valley floor. The International Space Station ticks faster than your watch on Earth. Each difference tiny, but undeniable. Follow these threads far enough, and you arrive at the most extreme curve in space-time. A singularity hidden behind an event horizon. A place where the equations themselves bend, and our intuition breaks completely. Here, relativity does not just predict slow clocks. It predicts that from the outside, falling into a black hole is like falling out of time. An object never appears to cross the horizon. It simply fades, stretching towards stillness, while to itself it plunges inward without pause. This is the bizarre beauty of relativity. It shows us that time is not absolute. It is not uniform. It is shaped by speed, warped by gravity, and at the edge of a black hole, stretched to the breaking point. And so, as we move forward, we will follow relativity to its ultimate test. We will approach the horizon of a black hole and watch time itself unravel. Part 3. Time dilation in motion. If relativity taught us anything, it is that speed bends time. The faster you move, the slower your seconds pass compared to those at rest. This sounds like science fiction, but it has been tested again and again. One of the first proofs came from the Hafele-Keating experiment in 1971. 4 cesium atomic clocks were flown around the world on commercial airliners. 2 flew eastward, 2 flew westward, while matching clocks remained at the US Naval Observatory. When reunited, the airborne clocks disagreed with those on the ground. The difference was tiny, nanoseconds, but exactly what relativity predicted. This experiment was not a curiosity. It was a demonstration that motion changes time itself. Even nature runs the same experiment constantly. High-energy particles called muons rain down from cosmic rays striking Earth's atmosphere. At rest, muons decay in microseconds. Yet when accelerated to near-light speed, they survive far longer, long enough to be detected deep underground. Their lives stretch out because their clocks slow compared to ours. To visualize this, imagine a spaceship traveling at 99% the speed of light. For the crew inside, a journey to a star 10 light-years away might feel like only a few years. But for those left on Earth, decades would pass. When the travelers returned, they would find themselves younger than their own twins. This is not imagination. It is the twin paradox, a natural consequence of relativity. And here is the strange part. To the travelers, nothing seems unusual. Their hearts beat normally. Their meals take the same time to cook. Their conversations feel unchanged. It is only in comparison with those who stayed behind that the difference is revealed. This is the essence of relativity. Each observer has their own time, their own reality, woven consistently within their own frame of reference. Only when 2 observers meet again do the differences become visible. Even today, astronauts aboard the International Space Station live this reality. Orbiting at 28,000 kilometers per hour, their clocks run just a bit slower than ours. Over a 6-month mission, the difference is only milliseconds. But it is there, written into their bodies, carried back to Earth as proof. Speed stretches time, and the closer to light speed we travel, the greater the stretching becomes. In motion, seconds are not what they seem. They are malleable, elastic, fragile threads pulled by velocity itself. But motion does more than stretch seconds. It reshapes our understanding of distance itself. To a traveller nearing light speed, the universe contracts. Stars that seem impossibly far from Earth draw closer, compressed along the direction of motion. This is length contraction, the twin sibling of time dilation. Together, these effects preserve the one inviolate rule: nothing outruns light. To the crew on their near-light ship, the journey feels brief, because both time and distance have reshaped themselves. To the watchers back home, the same journey consumes decades. Each perspective is true, each reality consistent within its own frame. This relativity of time is not just an intellectual puzzle. It carries profound consequences for how we imagine our future. For interstellar travellers, time dilation is no threat. It is a gift. It means that the long road to distant stars can be shortened, not by changing the stars, but by changing the traveller's time. The price, of course, is asymmetry. Those who leave will return to a world older than themselves. Families long gone, civilizations perhaps transformed. The twin paradox is not only physics, it is also tragedy. But here on Earth, even without starships, the universe still whispers its relativistic truth. Our planet spins, our satellites orbit, our spacecraft voyage outward, and each one ticks to its own rhythm of time. In laboratories, particle accelerators push protons to speeds where their lifetimes stretch 1,000-fold. Physicists watch as fleeting particles live far beyond their natural span, their decay postponed by the dilation of time. Even our own heartbeat, though too slow to measure without instruments, is bound to the same principle. Were we to sprint across space at near light speed, the beat of our hearts would appear slowed to a distant observer, while to us it would feel unchanged. This duality is what makes time dilation so strange. It is both real and hidden. Undeniable in experiment, yet invisible to those experiencing it. And so, time in motion is not an abstract curiosity. It is written into the flight paths of satellites, the survival of cosmic particles, the rhythm of space travel itself. Speed bends the seconds, and the faster you move, the more those seconds stretch, until near light, time itself becomes nearly still. Here, in motion, we glimpse the first doorway to eternity. Part 4. Gravity and time. If speed can bend the seconds, so can gravity. Einstein's general theory of relativity revealed this hidden truth, that gravity is not a force pulling objects down, but the curve of space-time itself. Mass tells space how to bend. Space tells time how to flow. And together they create the strange choreography we call gravity. To imagine this, picture a stretched fabric. Place a bowling ball in the centre, and the fabric dips. A marble rolling nearby curves inward, not because the ball pulls it, but because the fabric itself is bent. So it is with planets orbiting stars. They follow the curve of space-time, as rivers follow the slope of a valley. But here is the deeper strangeness. Where gravity is strong, time itself slows. A clock on a mountaintop ticks slightly faster than one in a valley. An astronaut hovering above Earth ages differently than one standing at sea level. The differences are small, measured in billionths of a second. Yet they are measurable, undeniable, real. These variations were first glimpsed in delicate experiments with atomic clocks. One such test took a clock up a tall tower, and compared it to one left below. The higher clock ticked faster. Time flowed more freely in the weaker pull of gravity. It may sound absurd. How could altitude change time? But consider what Einstein's equations demand. To keep light speed constant, space-time must balance itself. Where gravity bends space, it must also bend time, stretching it in the presence of mass. We see this effect not only in laboratories, but in the universe at large. Light escaping from a massive star shifts red, its waves stretched by the slowing of time. This is gravitational redshift, the fingerprint of warped time woven into starlight. The deeper the gravity well, the stronger the distortion. A neutron star, crushed to the size of a city but heavier than the sun, slows time by measurable amounts. Its immense density drags at the seconds themselves. And at the extreme lies the black hole, a singularity wrapped in space-time so steep that nothing, not even light, can escape. Here, gravity does not just slow time, it brings it nearly to a halt, at least from the perspective of the distant observer. To approach this reality, we must understand gravity not as weight, but as geometry. Every mass distorts the space-time around it. Every distortion is also a slowing of time. And in that slowing lies the doorway to the strangest phenomena of the cosmos. But unlike the abstract fabric of a diagram, gravity's impact on time is something you live with every day. Standing on Earth, you're already within a gravity well. Your seconds are ever so slightly slower than those of a satellite drifting high above. To us, the difference is imperceptible. But to our technology, it is decisive. The GPS satellites that guide airplanes, ships, and your morning commute all must correct for the fact that their clocks tick faster in orbit. Without those corrections, your location on Earth would drift kilometers off in a single day. Every navigation app is a daily tribute to Einstein's insight. Yet the lesson runs deeper than engineering. It forces us to ask, what is a second? A cesium atom oscillating? A planet turning? A star circling a galaxy? All of these measures are bound to space-time, and all are bent by mass and motion. Consider the International Space Station. Astronauts live just outside Earth's densest gravity, so their clocks tick faster. But they also race at 28,000 kilometers per hour, so their motion slows them down. One effect cancels part of the other. The balance is delicate, a daily tug-of-war between gravity and velocity. And so, the astronaut who spends months circling the planet returns younger by a fraction of a second. A whisper of difference, but a difference nonetheless. Now, imagine turning up the dial. Move from Earth to a neutron star. Here gravity is 10 trillion times stronger. An observer on its surface would experience time slowed dramatically compared to one watching from afar. To the distant eye, their heartbeat drags, their voice lengthens, their life is drawn out. Push further, and you reach the black hole. At the event horizon, time to the outside world halts. To the falling traveller, everything seems normal. But to those left behind, the traveller is frozen at the edge, a ghost of light stretched thinner and thinner. Gravity does not simply slow time. It divides it. Each vantage point holds its own truth, woven into the fabric of the cosmos. And here lies the paradox that defines our universe. The stronger the pull of gravity, the weaker the flow of time. Every mountain, every planet, every star is a silent sculptor of seconds. Every step closer to mass is a step deeper into slower time. Gravity shapes not only the paths of planets and the light of stars, but the beating of every heart, the tick of every clock, the rhythm of every life. To fall into gravity is to fall into another time. Part 5. Approaching a black hole. Far across the Milky Way, stars orbit a hidden giant. At the centre lies Sagittarius A, a supermassive black hole 4 million times heavier than our Sun. Though invisible, its presence is undeniable. Gas clouds whirl around it. Stars slingshot at tremendous speeds, bound to its invisible grip. To approach such an object is to approach the edge of reality itself. Imagine piloting a spacecraft inward. At first, everything seems ordinary. The black hole is distant. The stars still familiar. But as you draw nearer, the light begins to bend. Background stars stretch into arcs, their photons dragged along the warped geometry of space-time. Your onboard clocks tick normally, your heartbeat steady, your breath calm. But to distant observers, watching through telescopes, your seconds begin to stretch. Signals you send take longer to arrive. Your image slows, redshifts, fades. The closer you move, the stranger the view. Ahead, the black hole does not appear as a simple void. Instead, you see a sphere of darkness surrounded by a glowing halo. This is the accretion disk, gas spiraling inward, heated to millions of degrees, shining in furious radiation. Around it lies the photon sphere, where light itself is trapped in orbit. Here, photons circle the black hole like planets around a star, before escaping or plunging inward. To your eyes, this creates the illusion of a glowing ring, a circle of fire around eternal night. Yet what is most unsettling is not what you see, but what you feel. The pull grows stronger with every kilometre. Tidal forces begin to whisper through your body. Your head and feet no longer share the same gravity. A subtle stretch, not yet painful, but a reminder of the immense gradient of force that lies ahead. And through it all, time continues its strange transformation. To you, it flows without change. To the universe outside, it slows, redshifts, distorts. The deeper you fall, the greater the divide between your moments and theirs. This is only the beginning. The threshold lies ahead, the event horizon, the point of no return. Cross it, and no signal, no light, no memory escapes. Approaching it is not only a journey into gravity, but a journey into the very nature of time itself. As the horizon nears, the universe begins to distort. The stars behind you seem to pile together, their light dragged and twisted into arcs. Ahead, the void swallows more of the sky. The black hole does not simply appear larger, it becomes the sky itself. Your instruments strain to keep up. Clocks aboard the ship tick normally in your frame, but their signals sent outward reach distant observers slowed and stretched. To them, your seconds lengthen toward infinity. To you, the mission log is steady, heartbeat ordinary. This duality is the essence of relativity. Two realities, both true, coexisting but never reconciling. The traveller falls. The watcher sees them suspended, forever at the edge. The closer you drift, the stronger the tidal stretch becomes. Feet pulled harder than your head, molecules tugged apart by gradients in gravity. Physicists call it spaghettification, a word both absurd and terrifying. And yet, even here, relativity preserves dignity. To you, the crossing of the horizon would feel unremarkable. No flash, no wall, no sudden rupture. One moment you float in the universe. The next, the universe floats only behind you, forever beyond communication. This contradiction is at the heart of black holes. They are not merely objects of gravity. They are horizons between perspectives. One truth for the outside, another truth for the inside. Approaching a black hole is approaching this divide, a frontier where the flow of time itself fractures into irreconcilable realities. From here onward, every step deeper is a step further into the unknown. And yet, we must continue. Because only by following this descent do we learn what it means for time to bend, to stretch, to almost stop. In the next part, we will step to the threshold itself, the event horizon, the point where time becomes more than relative, the place where time becomes silence. Part 6. The event horizon, There is a boundary in the universe unlike any other. Not a wall you can touch, not a line you can mark with paint or stone, but a horizon, the event horizon of a black hole. It is the point of no return, the invisible surface where escape velocity equals the speed of light. Cross it, and no signal, no light, no memory can ever leave again. From the outside, the horizon looks like the edge of forever. A perfect sphere of darkness, ringed by distorted starlight. A lens to the cosmos, bending light into strange arcs. The closer you drift, the more the stars appear to swirl, drawn into impossible patterns. But the true strangeness is not in the view, but in the flow of time. For a distant observer you never cross. Your approach slows, your signals redshift, your image freezes on the edge. It is as if you are suspended, caught between motion and stillness. For you, inside the ship, there is no pause. The horizon passes silently. No flash, no jolt, no barrier. Just the smooth continuation of your fall. To you, the crossing is unremarkable. To the outside, it never occurs. This is the paradox of the event horizon. A boundary where time itself splits into two realities. One for the traveller, one for the watcher. And both are true. Einstein's equations leave no escape. To maintain the speed of light as the cosmic limit, the flow of time must stretch infinitely at the horizon. Every second inside becomes unreachable outside. Every moment of your descent is hidden beyond eternity. The horizon is not only the edge of space, it is the edge of knowable time. And to approach it is to approach the greatest silence in the universe. But what happens once you have crossed? From the traveller's view, the horizon is behind them now, sealed forever. The outside universe still exists, but its light grows dim, its signals weaker, its voice is stretched thin until silence. To the traveller, time flows forward as always. Seconds follow seconds. Heartbeat follows heartbeat. Yet those seconds are now cut off from the rest of the cosmos. They are private, sealed within a horizon that no message can breach. To the distant observer, the story is different. They never see the crossing. Instead, they watch a fading ghost. Signals redshift until their wavelengths stretch beyond detection. The traveller becomes an echo smeared across eternity, a picture trapped forever on the edge. This dual perspective unsettles us, because it challenges the idea of a single reality. Was the crossing smooth and unremarkable? Or did it never happen at all? Both are true. Both are real. The event horizon is not a physical barrier, but a boundary of information. It is the place where knowledge ends. For everything that happens beyond it, the universe outside receives no report. In that sense, the horizon is not just an edge in space, it is an edge in truth. Physicists have wrestled with this idea for decades. Stephen Hawking showed that horizons are not absolute prisons. Quantum effects allow them to radiate, slowly evaporating across unimaginable timescales. This Hawking radiation blurs the horizon's role, suggesting that information may not vanish, but seep outward in ways we do not yet understand. Still, for the traveller, none of this matters. Their fall continues. Inside, there is no sense of slowing, no sense of freezing. The event horizon passes without drama. The true mysteries lie deeper. For the watcher outside, the story ends here. For the traveller, the story is only beginning. This is the enigma of the event horizon. Two narratives, two truths, divided by a line no signal can cross. And so, the horizon stands as one of the greatest symbols of relativity. A place where physics forces us to accept paradox. A reminder that reality may depend on where you stand. In the next part, we will move deeper still. Beyond the horizon, where gravity intensifies, where space narrows, and where the traveller meets the crushing force of spaghettification. Part 7. spaghettification and tidal forces. As you pass the event horizon, a new reality asserts itself. The black hole is not only a well of slowed time, it is also a landscape of violent gradients. Gravity here is not gentle, not uniform. It changes with every centimetre. Your head and your feet do not feel the same pull. Your atoms are tugged with different strengths. This difference is what physicists call tidal force. It is the same phenomenon that moves the oceans of Earth. As the moon's gravity pulls harder on one side of the planet than the other. But near a black hole, tidal forces are no gentle tide. They are violent beyond imagination. If you fell feet first, your lower body would feel an acceleration far stronger than your upper. Your form would begin to stretch. At the same time, you would be squeezed from side to side, narrowed as space itself funnels inward. The combined effect is grotesque elongation. A human body turned into a thread of matter thin and long. Physicists, with dark humour, call it spaghettification. At first, the stretching is subtle. It would not be noticed until you approach dangerously close. But once inside the horizon of a stellar mass black hole, the forces would grow irresistible in seconds. Muscles tear, bones yield, molecules separate. You would be unravelled, drawn into an ever thinner strand. For supermassive black holes, the story is stranger. Their horizons are vast, millions of kilometres across. The tidal forces at the boundary are weaker, spread across the immense scale. You could cross the event horizon of a giant like Sagittarius A without immediate destruction. For a time, you would survive, falling deeper before the forces grew unbearable. This difference between stellar and supermassive black holes is crucial. It means that in theory, an astronaut could cross the horizon of a supermassive black hole alive. Their last moments would not be instantaneous obliteration, but a descent through warped space and stretched time. But survival is relative. Because the closer you approach the singularity, the sharper the tidal gradient becomes. No matter how vast the black hole, the final fate is the same, stretching into infinity. Spaghettification absolute. And yet, even this grotesque destiny is bound to time's paradox. To you, it happens in a finite span, seconds, minutes, perhaps hours. To the outside universe, your final fall is drawn out into eternity, never quite complete. Inside and outside, two stories unfold. Both true, both irreconcilable. This is the riddle of tidal forces in the heart of relativity. And as we fall, we carry this riddle deeper still, toward the singularity itself. The deeper you fall, the sharper the divide becomes. Each atom in your body feels its own tug of gravity. Molecules are strained. Cells no longer share the same clock. The body that once lived in harmony is stretched into a cascade of parts, each pulled into the abyss at its own pace. Spaghettification is a gruesome word, but it captures the essence. Not a sudden explosion, but a patient unravelling, like dough being rolled thinner and thinner, until it becomes strands. This is what happens when gradients of gravity grow stronger than the bonds of matter. For a stellar mass black hole, this disassembly would happen long before you reach the singularity. A person, a ship, a planet, all reduced to ribbons of atoms. For a supermassive black hole, the stretching may begin only much deeper inside, but the end is the same. And this destruction is not only physical, it is temporal. As you're pulled into strands, your time is pulled too. Signals you try to send are broken, fragmented into ever weaker echoes, until even light cannot carry your voice outward. From the outside, the story is stranger still. The observer never sees you torn apart. Instead, they see only your image frozen on the horizon, red-shifted into darkness, while your fate beyond the edge remains hidden. Two truths never reconciled. It is a reminder of relativity's greatest lesson, that what is real depends on where you stand. To the traveller, there is a fall, a stretch, an ending. To the watcher, there is only stillness, a ghost suspended on the brink. And so, spaghettification is more than a brutal death by gravity. It is the ultimate illustration of time torn into two stories. As we leave this part, we carry the unsettling image of a universe where even identity is unravelled, where the laws of physics do not preserve the unity of a body or a moment, but draw them apart, thread by thread, second by second. And yet, we are not done, because beyond spaghettification lies the singularity itself, the place where our equations collapse, and where time may lose all meaning. Part 8. Time travel implications. If speed can bend seconds, and gravity can stretch hours, then falling into a black hole is not only a descent into darkness, it is also a journey into the future. For relativity leaves us with a strange possibility. Time travel does not require a machine, only motion and gravity. To live faster than others, or to fall deeper than others, is to leap ahead in time. Consider the astronauts circling a black hole. Each orbit near the horizon slows their clock compared to distant observers. To them, days pass. To the universe, centuries might unfold. When they finally return, they step into a future they could never have reached by waiting. This is time travel by dilation. One way, irreversible. A voyage into tomorrow without the power to return to yesterday. In a sense, we are all time travelers already. Every second carries us forward, relentlessly into the future. But relativity shows us shortcuts. By moving faster, or by sinking into deeper wells of gravity, we can let others age while we remain younger. This is not speculation. It is measured fact. The astronaut who spends a year in orbit will return to find their twin age slightly more. The effect is small near Earth, but in the heart of relativity, it becomes immense. And so, black holes are not only destroyers, they are also time machines. Step too close, and you step forward across ages. From your view, minutes have passed. From the galaxy's view, civilizations may have risen and fallen. This possibility reshapes our imaginations. When we ask, can we travel through time? The answer is yes, but only forward. And the cost of such a journey is isolation, because the farther you leap ahead, the more you leave behind. To orbit a black hole is to orbit destiny. To fall into one is to fall out of history. This is the time machine relativity gives us. Not the fantasy of rewinding the past, but the reality of accelerating into the future. But time dilation does not only move travellers forward, it raises deeper questions about causality, memory and destiny. If you leap centuries ahead by orbiting near a black hole, you do not only leave behind your family and your world, you also abandon the very culture that gave meaning to your life. Every language you spoke may have vanished. Every map you trusted may be unrecognizable. Time travel is not just physics. It is exile. This possibility haunts us in fiction. In movies, we dream of voyaging forward, meeting distant futures, or even looping backward, rewriting mistakes. But relativity grants only the first. You may skip ahead, but you can never return. And so, time dilation is a kind of one-way ticket. It offers glimpses of futures you could never reach otherwise, but at the price of everything familiar. Still, the concept tempts us. Imagine a civilization orbiting close to a black hole, using its time dilation as a shield against cosmic catastrophe. From their view, perhaps only years pass, while outside, millions of years unfold. Such a people could outlast galaxies, surviving the ages by slipping through the cracks of time. Yet even here, the paradox deepens. For the rest of the universe, these time travelers would be frozen ghosts, moving in slow motion, barely alive. To themselves, they would feel unchanged. The two perspectives never meet, yet both are real. This is the heart of relativity's time travel. Not machines of fantasy, but natural consequences of space-time's geometry. A truth stranger, and perhaps more haunting than fiction. And so, when we ask, can we time travel? The answer is yes. But it is not the playful yes of rewinding a tape. It is the solemn yes of stepping into a future you cannot return from. For now, this remains only a thought experiment. We have no ships to orbit horizons, no courage to fall knowingly into singularities. But the equations remain, whispering of what is possible. And as we leave this part, we carry both wonder and unease. Wonder that time itself can be bent and travelled. Unease that such travel is one way, and that its cost may be everything we know. In the next part, we will ask the hardest question of all. What lies beyond the horizon, deeper than dilation, closer to the singularity where even time itself may end? Part 10. The Singularity. At the heart of every black hole lies a mystery. The singularity. A point where our equations collapse, and physics itself seems to falter. From Einstein's relativity, the prediction is stark. Matter falls inward without end. Space curves infinitely. Density rises without limit. And time itself, ends. But can infinity exist in nature? Or is the singularity not a real place, but a signal that our understanding is incomplete? To imagine the singularity, picture every atom of a star crushed into a volume smaller than a grain of sand. Now, shrink it further, and further still, until the concept of place itself breaks apart. Here, space-time is no longer a smooth fabric. It is torn, jagged, undefined. Relativity can describe the descent, but not the destination. Quantum physics whispers a different story. At the smallest scales, space-time may not be continuous. It may be granular, foamy, stitched from quantum threads. If so, the singularity may dissolve into something else. A core where gravity meets quantum mechanics in ways we cannot yet see. Physicists search for this union. A theory of quantum gravity. Some imagine loops of space-time woven together. Others picture vibrating strings in higher dimensions. All share one goal: to remove the impossible infinities at the heart of black holes. But for the traveller inside, theory offers no escape. Every path curves toward the singularity. Every second brings them closer. Here, time is no longer a river flowing forward. It is a whirlpool, dragging all matter, all light, all memory into its centre. The singularity is not just the end of a journey. It is the end of a story. The end of the universe's ability to record what happens next. And so, when we speak of singularities, we are not speaking of a place. We are speaking of the frontier of knowledge, the point where our mathematics asks questions we cannot yet answer. To fall toward the singularity is to fall into the unknown, a domain where human thought has not yet found footing, and where time itself may lose all meaning. The singularity is a paradox given form. It is predicted with certainty by the mathematics of relativity, yet it is forbidden by our instincts about nature. Infinity, after all, is not a measurement. It is a confession, a way of saying we do not know. What happens to matter once it crosses the final threshold? Does it compress into an infinitely small point? Or does quantum mechanics step in, revealing a hidden structure where relativity alone cannot reach? Some theories suggest that singularities may not exist at all. Instead, matter may bounce, rebound through a hidden channel of space-time, perhaps into another universe entirely. Others imagine black holes as seeds of creation, giving birth to new cosmic regions beyond our sight. In loop quantum gravity, the geometry of space-time itself becomes discrete, made of tiny loops that prevent infinite collapse. In string theory, vibrating strings in higher dimensions may smear out the singularity, replacing the point of infinity with something more tangible. But as of now, these are whispers in the dark, possibilities without proof. For the traveller inside, such speculation is irrelevant. The singularity is not a theory. It is their future. Every second the tidal forces grow. Every breath brings them closer to the limit where physics breaks. From the outside, the story has long since ended. The traveller is frozen on the horizon, their light stretched into invisibility. But inside, their journey is not yet complete. They fall toward the singularity as we fall toward tomorrow. Unstoppable, inevitable, unreturning. The singularity is more than a place. It is the end of prediction, the end of every law we have written, and perhaps the beginning of something new, a chapter of physics we have not yet learned to read. To approach the singularity is to stand at the edge of knowledge itself. And to cross it is to vanish not only from the universe, but from understanding. Still, even as we confess our ignorance, there is awe in this mystery, for within the singularity may lie the deepest truths of the cosmos, how space and time began, and how they may one day end. Part 11. Hawking radiation and evaporation. Until now, the black hole has seemed like the ultimate prison, an abyss that swallows everything, from light to matter to memory. But in 1974, a young physicist named Stephen Hawking revealed something astonishing. Black holes are not entirely black. They glow. This glow is not like the blaze of a star. It is faint, almost imperceptible, but it is real. It comes not from inside the horizon, but from the strange fabric of empty space itself. Quantum mechanics tells us that emptiness is never truly empty, even in a perfect vacuum. Tiny pairs of particles flicker into existence. A particle and its mirror, a particle of matter and its partner of antimatter. They are called virtual particles. Most of the time, they annihilate one another almost instantly, returning their borrowed energy to the void. But near the event horizon, something different can occur. One particle falls inward, the other escapes. To the outside universe, it appears as if the black hole itself has emitted a particle of radiation. This is Hawking radiation, a whisper of energy leaking from the most secretive objects in the cosmos. The implications are profound. If black holes radiate energy, they also lose mass. Slowly, silently, across unthinkable stretches of time, a black hole evaporates. The process is impossibly slow for giants. A black hole the mass of a star would take longer than the age of the universe to evaporate. A supermassive black hole could last trillions upon trillions of years. But eventually, even they will vanish, leaving behind only a faint sigh of radiation. This changes everything we thought we knew. The black hole is not eternal. It is mortal. It has a lifespan. And yet, this discovery opens new paradoxes. If black holes evaporate, what happens to the information they swallowed? Does it vanish too? If so, the laws of quantum mechanics, which demand information must never be destroyed, would break. Thus began the greatest puzzle of modern physics, the black hole information paradox. But at its heart lies a haunting truth. Even the darkest objects in the universe are not permanent. Even horizons whisper. Even singularities fade. To watch a black hole evaporate is to watch time's patience outlast gravity itself. But Hawking radiation does more than make black holes mortal. It forces us to face one of the most profound paradoxes in science. When a black hole evaporates, what becomes of the information it has consumed? Every book, every signal, every atom that has ever fallen in, are they gone forever? If so, the universe itself breaks its most sacred rule. In quantum mechanics, information can never be destroyed. It can be scrambled, hidden, diffused, but it must persist. This conflict between relativity and quantum mechanics is called the information paradox. And it has shaken physics for half a century. Some propose that the information is encoded in the Hawking radiation itself, subtle correlations hidden in the outgoing particles. Others argue that it lingers on the horizon as a hologram, a surface storing the secrets of everything that falls inside. This idea gave rise to the holographic principle, the notion that our three-dimensional universe might itself be a projection, its true information written on a distant boundary. Still others suggest even stranger fates, that black holes may open bridges to other regions of space-time. That information may leak into hidden dimensions. Or that new physics, deeper than both relativity and quantum theory, must rewrite our understanding of reality itself. Yet for all the speculation, one fact is inescapable. Black holes do not last forever. Given enough time, they fade. The universe, once dominated by blazing stars and collapsing giants, will one day be dotted with only their faint, evaporating echoes. Imagine a cosmos trillions of years from now. The stars long extinguished. Galaxies dissolved. Only black holes remain, slowly hissing their last radiation into the dark, each one shrinking, until, with a final burst, it vanishes. In that far future, there will be no suns, no planets, no warmth. Only the dying whispers of Hawking radiation, marking the end of gravity's reign. And so, black holes, once thought to be eternal monuments of the cosmos, are revealed as transient after all. Born in collapse, they live across unimaginable ages, and then fade, leaving no trace but faint echoes of the laws they obeyed. To contemplate this is to glimpse the ultimate patience of time. Time that waits, not for centuries, not for eons, but for eternities. Hawking's discovery transformed our view of the universe. It showed us that even the darkest objects glow, that even death is temporary, that nothing, not even a black hole, is beyond change. And in that glow, faint though it may be, lies the promise of answers to the deepest riddles of reality. Part 12. Black Holes and the End of Time. When we look at a black hole, we are not only looking at gravity, we are looking at time itself brought to its edge. Around stars, time flows almost as we expect. Around planets, clocks differ by tiny fractions of a second. But near a black hole, time itself begins to tear. It slows, stretches, and finally seems to stop. To the outside universe, a black hole is a frozen moment. Everything falling in appears locked at the horizon, forever unfinished. To the traveller, time flows forward, but only toward the singularity. Two truths, both real. This duality leads to a haunting thought. Black holes are not only destroyers of matter, they are destroyers of time itself. Consider the far future of the cosmos. Stars will burn out, galaxies will fade, and what remains will be black holes, patiently waiting. Their horizons marking the places where time slows nearly to silence. In that deep future, time will be measured not by the ticking of suns, but by the slow evaporation of black holes themselves. Their Hawking radiation will be the last whisper of physics still at work. This suggests something profound, that black holes may be the ultimate rulers of time. Not because they endure forever, but because they define the final chapters of the universe's clock. For when the last black hole dies, what then remains of time? If no clocks tick, if no processes unfold, if no events succeed one another, can we still say that time exists? Here, physics meets philosophy. For time, as we measure it, is only the record of change. If all change ends, then time itself may end too. And so, when we speak of black holes, we speak not just of gravity or collapse. We speak of the fate of time itself. But perhaps there is another way to see this. Perhaps black holes are not the destroyers of time, but the keepers of its last record. Every star they swallowed, every planet they consumed, every photon that fell into their depths, all of it remains in some form, encoded in the curvature of their horizons, imprinted in the slow sigh of their hawking radiation. In this view, black holes are not just tombs. They are libraries. Vast, silent, almost impossible to read, but libraries nonetheless. If this is true, then the final age of the cosmos, the age of black holes, may also be the final age of memory. When the last hole evaporates, not only does gravity's last monument disappear, but perhaps the last archive of the universe is erased. Imagine that future. No stars to mark the hours. No galaxies to record the centuries. Only fading horizons dissolving into faint heat. When the final one vanishes, time itself may lose its meaning, for there will be no rhythm left to measure, no change left to count. This is the ultimate irony. Black holes, born from the collapse of stars, may outlive the stars, the galaxies, and the universe itself. And in doing so, they may define not only the end of matter, but the end of time. And yet, there is mystery here. For if black holes evaporate, they may leave behind something unexpected. A remnant, a quantum seed, a clue to physics deeper than either relativity or quantum mechanics can currently explain. So perhaps the end of time is not an erasure. Perhaps it is a transformation. An end that becomes a beginning, just as the death of stars gave birth to black holes. In this way, black holes are more than the final pages of cosmic history. They may be the ink with which the next story is written. And as we stand here, contemplating the end of time itself, we are reminded of a deeper truth, that every end carries within it the shape of something new. Part 13. Observational Evidence and Black Hole Imaging. For centuries, black holes were only ideas. Mathematical ghosts predicted by Einstein's equations but unseen by any eye. Many doubted they could be real. How do you observe something that emits no light? How do you photograph an object designed by nature to hide itself? The answer, paradoxically, is to look not at the black hole itself but at what surrounds it. Gas spiralling into the abyss heats up, glowing brighter than the core of stars. Jets of plasma erupt from magnetic fields twisted at the edge of the horizon, streams of matter moving at nearly the speed of light. And stars themselves are caught in orbits so fast, so tight, that only an invisible giant could explain their dance. It was in this way that astronomers discovered the monster at the centre of our own galaxy, Sagittarius A. By watching stars whirl around an unseen point, they measured a mass 4 million times greater than our Sun compressed into a space smaller than our solar system. Nothing visible, nothing shining, only the undeniable grip of gravity. And then, in 2019, the impossible became visible. The Event Horizon Telescope, a global network of radio observatories linked into one planet-sized eye, captured the first direct image of a black hole. A shadow ringed by fire. The silhouette of the void itself, outlined by glowing gas on the brink of no return. It was the black hole at the heart of galaxy M87, 55 million light-years away. The image was grainy, imperfect, yet historic. For the first time, humanity had looked into the abyss and seen its outline. That shadow told us more than theory ever could. It confirmed relativity's predictions with astonishing accuracy. The size of the horizon, the bending of light, the structure of space-time at its most extreme. This was not only an image, it was a bridge between imagination and reality. A reminder that black holes are not just abstractions on chalkboards. They are out there, real, monstrous, and beautiful. And it was only the beginning. For we are now entering an era where telescopes and detectors can do more than glimpse shadows. They can listen to the universe itself through the ripples of space-time that black holes create. But light alone is not enough. To truly understand black holes, we needed to learn how to listen. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected a signal unlike any ever recorded. A faint ripple, stretching and squeezing space-time itself, as two black holes spiraled into one another and collided. The event lasted less than a second. But in that instant, the merger released more energy than all the stars in the observable universe combined. Not in light, not in particles, but in gravity itself. For the first time, humanity had heard the universe. Not through photons, but through waves in the very fabric of reality. This was Einstein's century-old prediction made real, that accelerating masses create ripples in space-time, waves that travel across the cosmos at light speed. Since then, detectors on Earth have captured dozens of such events. Black holes colliding, neutron stars merging, cataclysms so distant and yet so powerful that their echoes reach us across billions of light years. Together with the Event Horizon Telescope, these discoveries have transformed black holes from theory into observable fact. We can now see their shadows, trace their jets, watch their orbits, and even hear their collisions. Each piece of evidence draws the picture sharper. Black holes are no longer whispers of mathematics. They are real, measurable, and testable. They are laboratories of the extreme, where relativity and quantum theory are pushed to their breaking points. And perhaps most profoundly, our ability to see and hear them reminds us of something deeper, that the universe is not silent. It is alive with signals, waiting for us to learn the right way to listen. With every image captured, with every gravitational wave detected, we take one step closer to understanding the most mysterious objects in the cosmos. But the deeper we look, the more questions emerge. For while observation confirms relativity's strength, it also sharpens the paradoxes we cannot yet solve. The horizon remains a wall of silence, the singularity remains hidden, and the question of information, whether black holes destroy or preserve it, remains open. We have seen their shadows, we have heard their collisions, but their secrets are still beyond our grasp. And so, black holes remain both the most proven and the most mysterious of cosmic objects. Visible, measurable, undeniable, and yet still keeping their final truths locked away beyond the horizon. Part 14. Black holes in culture and human imagination. Long before telescopes could glimpse their shadows, black holes lived in the realm of myth. Ancient cultures spoke of cosmic abysses, mouths of monsters that swallowed suns, dark caverns in the heavens where time itself seemed to vanish. In Norse sagas there were wolves that devoured the sky. In Hindu cosmology, the cycles of destruction and rebirth echoed the idea of collapse and renewal. In every tradition, shadows held a special power, fear and awe bound together. When Einstein's equations hinted at the possibility of frozen stars in 1916, they seemed less like physics and more like folklore written in mathematics. The term black hole itself, coined in the 1960s, carried the poetry of mystery, a name that at once evoked absence, inevitability, and danger. As the science deepened, so too did the symbolism. Black holes became metaphors for death, for the unknown, for obsessions that consume everything drawn too close. Writers and poets borrowed their gravity to describe grief and longing. Philosophers saw in them a reflection of the limits of knowledge. In popular culture, black holes have become stage sets for our imagination. From pulp science fiction of the 20th century to modern films like Interstellar, they serve as portals to other times, other places, or other truths. The sight of a spaceship falling toward the horizon has become a visual shorthand for mystery itself. And yet, even as Hollywood dramatizes them, the reality is stranger than fiction. No script could invent spaghettification. No stage could capture the silence of time stretched into eternity. It is a reminder that black holes need no embellishment. Their true physics is already more haunting than our myths. But the cultural role of black holes goes deeper still. They are not only symbols of destruction, they are also mirrors of our curiosity. Every time we tell stories about them, we're also telling stories about ourselves, about our fear of endings, about our desire to know what lies beyond the visible, about our struggle to face the limits of our understanding. Thus, black holes occupy two worlds. In science, they are equations, telescopes, and data. In imagination, they are metaphors for love, death, destiny, and infinity. In both, they remain the same, enigmas that draw us closer, even as they warn us that crossing the horizon may cost us everything. Black holes have become icons of the unknown. They haunt literature, film, and philosophy not just as astrophysical objects, but as symbols of mystery itself. Writers use them to describe grief so deep it swallows everything. Artists paint them as wounds in the canvas of reality. Musicians borrow their names to capture feelings of weight and inevitability. In cinema, black holes are doors. In Interstellar, the black hole Gargantua became not only a backdrop, but a character, its immense gravity bending both space and story, forcing humans to face the cost of time dilation. In countless other works, the horizon becomes a metaphor for the boundaries of knowledge, for the threshold we cross when we risk everything to discover something new. Even language itself bends around them. We call overwhelming tasks black holes of attention. We call addictions black holes of desire. The metaphor is universal, a pull that is irresistible, a darkness that consumes. And yet, woven into this darkness is a strange beauty. Because to imagine a black hole is also to imagine courage. The courage to look where no light escapes. The courage to ask questions with no easy answers. That is why black holes endure not only in equations and telescopes, but in poetry, novels, music, and myth. They remind us that science is not just calculation. It is also imagination. For in the end, black holes stand as symbols of the human condition. We too are drawn toward mysteries. We too live at the edge of horizons we cannot cross. And like those who gaze into the abyss, we are both terrified and fascinated by what lies beyond. In culture, as in physics, black holes teach us this: that mystery is not the end of understanding, but its beginning. Part 15. Conclusion: Falling into Eternity. We began with a simple question. What happens when we fall into a black hole? The answer, as we have seen, is not simple at all. It is a journey through paradox, science, imagination, and time itself. To the outside world, the fall is eternal. To the traveller, it is brief. To relativity, both are true. Along the way, we have seen clocks slow, light stretch, bodies unravel. We have touched the singularity, where space collapses and time ends. We have traced the faint glow of Hawking radiation, a whisper that black holes themselves do not last forever. And beyond the mathematics, we have seen what black holes mean to us. Symbols of fear and fascination, mirrors of our longing to know what lies beyond. Poetic reminders that the universe holds mysteries too vast for easy answers. Black holes are physics at its most extreme. They test the boundaries of Einstein's relativity. They challenge quantum mechanics. They force us to confront what we do not yet know. But they are also invitations. Invitations to curiosity, to humility, to the understanding that our universe is not just stranger than we imagine, it is stranger than we can imagine. To fall into a black hole is not only to fall into gravity, it is to fall into mystery, into the silence of horizons, into the stillness where time unravels, into eternity itself. And yet, perhaps the true meaning is not in the fall, but in the act of asking. For every time we imagine the journey, we remind ourselves of the power of wonder. Wonder that drives us to build telescopes the size of planets. Wonder that tunes detectors to hear the universe whisper. Wonder that turns equations into poetry. In this way, black holes are not just cosmic objects, they are teachers. They teach us about physics. They teach us about limits, and they teach us about ourselves. Because like the horizon, we too live at an edge of knowledge, an edge of understanding, an edge of time. And every question we ask, every observation we make is a step toward crossing that horizon, not into destruction, but into deeper understanding. So perhaps falling into a black hole is not an ending after all. Perhaps it's the most profound reminder that endings and beginnings are only perspectives on the same truth. The truth that the universe is endless in its capacity to surprise. The truth that time itself is fragile, relative, and astonishing. And the truth that wonder endures long after stars fade, long after black holes vanish, long after time itself runs out. In the end, black holes are more than astrophysical objects. They are reminders. Reminders that the universe is larger, stranger, and more mysterious than our brief lives can ever fully grasp. We gaze at them from across light years. We measure their shadows with telescopes the size of Earth. We record their collisions as faint ripples in space-time, yet they remain beyond reach. And perhaps that is their true gift. For black holes show us the power of humility, that even in an age of science, we must learn to live with mystery. That not all questions have answers, but the act of asking reshapes who we are. To fall into a black hole is to confront paradox. Time stretches and ends. Matter vanishes and endures. Information is lost and preserved. Opposites coexist and truth lies in both. And perhaps this is why we are drawn to them. Because black holes are not only about death. They are about transformation. They remind us that endings are never final. They are horizons, gateways to realities we have yet to imagine. When the last star burns out, when the last galaxy fades, when the last black hole evaporates into silence, the universe will not remember us. But we, here, now, remember the universe. We carry its wonder in our questions, its vastness in our imagination, its mysteries in our longing. And in this way, we are not so different from black holes. We too bend time. We too contain secrets. We too hold within us infinities that others cannot see. So let us leave this journey not with fear, but with gratitude. Gratitude that the universe gives us questions so immense that even falling into eternity does not end them. For as long as we wonder, we have already crossed horizons. As long as we imagine, we have already travelled beyond. And as long as we seek, we will never stop falling, not into oblivion, but into awe.